velocity and acceleration in terms of displacement. So velocity, we have an equation for velocity, but instead of it being in terms of time, which is what we're used to seeing, it's now in terms of displacement. We know the second derivative with respect to time actually turns out to be the same as differentiating a half v squared with respect to x. Let me prove that. Okay, so we'll start with this. We know that acceleration is the same as dv to t. That formula is what we've been using so far because we've been mainly talking about equations in terms of time. So if I want to link velocity and time together, dv to t is what I'll use for acceleration. Okay, I could rewrite that using implicit differentiation, chain rule, whatever you want to call it. dv dx times dx to t. Okay, but dx to t is velocity. That one there is the one I tend to use, v dv dx. That's really useful when we want to link velocity and displacement together. Well, velocity I could rewrite. It is the derivative of a half v squared with respect to v. Well, now again, using implicit differentiation, chain rule, the dv's, if you like, cancel, and we get this d dx of a half v squared. Those two equations are the same thing. But I personally don't use the d dx of a half v squared unless they ask me to. I find the v to v dx one far more efficient for most of these problems. So a particle moves in a straight line, acceleration is given by 3 minus 2x. Find its velocity in terms of x, given that v equals 2 when x equals 1. All right, d dx of a half v squared is what they want me to use, maybe. But they're probably expecting me to use. So what happens when I use that? Well, we'll integrate both sides. I get a half v squared is 3x minus x squared plus a constant. Got to work out the constant. There must be a link in there somewhere between velocity and acceleration. When x equals 1, velocity equals 2. Constant turns out to be 0. So v squared, now multiplied by 2, is 6x minus 2x squared. That's not quite there because that's v squared. We want v. V then is plus or minus the square root of 6x minus 2x squared. This brings up the next question. How can I have two velocities? And the reason it can have two velocities is we've got rid of any mention of time. It's just displacement. So you can have two different velocities at the same point. One might be when I'm travelling in this direction, but then I might turn around and come back and I'm going in the other direction. And that's why you get plus or minus. Or, and this is why I prefer v to v dx, because as you know, I hate finding those constants. So using v to v dx, I can now separate the variables. So I get the integral of v to v is the integral of 3 minus 2x dx. The information they've given me, x is 1, v is 2. I want to link v and x together. Now, what ends up happening when you integrate the left-hand side, amazingly, you get half v squared. So you're still using that, but you're sort of getting it from the v to v dx. But because it's now a definite integral, I don't have to worry about finding the constant. I can now sub into that and get that a half v squared minus 2 is 3x minus x squared minus 2. The minus 2's cancel and I end up with the same equation. V squared is 6x minus 2x squared. I just think that's a neater, cleaner way of doing it. Notes. Velocity squared, of course, is going to be positive or 0. So it actually tells me a bit more about this little particle. Because that means 6x minus 2x squared is always greater than or equal to 0. That has a solution. 2x outside of 3 minus x is greater than or equal to 0. X is in between 0 and 3. So our little particle here has a very dull life. It's just going backwards and forwards between 0 and 3. That's all it does. But you can tell that from that equation. Particle's acceleration is given by 3x squared. Initially the particle is 1 unit to the right, travelling velocity of root 2. Now we're going to find the actual x in terms of t, even though acceleration is in terms of displacement. V to v dx, I'm not going to even bother with the half v squared this time. V to v dx is 3x squared. Separate my variables. Okay. Integrate. I've got half v squared is x cubed. Sub in. Half v squared minus 1 is x cubed minus 1. V squared is 2x cubed. So v is plus or minus root 2x cubed. This time I have to make a decision about whether it's plus or minus, because I'm now going to go and find the displacement equation. But to find that, I need an expression for dx to t. Is it plus? Is it minus? How do I tell? I'm going to use negative. I've got to satisfy the initial conditions. That's when we worry about, is it plus or is it minus? Remember that other one I didn't worry about it? Here I have to worry about it, because I'm going to use these initial conditions, so it needs to satisfy whichever equation that I'm using. Let's put that in the index form. Minus root 2x to the power of 3 on 2. Differential equation. Separate the variables. We have the integral of the t is minus 1 on root 2, the integral of x to the power of minus 3 on 2. So t is just going from 0 to t of the t, so I can write t down straight away. The right-hand side, I have minus 1 on root 2 times minus 2x to the minus half. There it is, almost. Because look what the question said. Find x in terms of t. We have t in terms of x. All right, let's make x the subject. So t plus root 2 will be root 2 on x. 2 on x will be t plus root 2 squared. X is 2 on t plus root 2 all squared. HSC question. Particles moving along x-axis from a position 2 meters to the right with an initial velocity of 5 meters per second and acceleration given by 2x cubed plus 2x. Show that the velocity is x squared plus 1. Okay. V to v dx is 2x cubed plus 2x. Separate the variables. The initial condition they've given me, 2 and 5. Integrate. Hang on. Shouldn't that be a half v squared? Do you see what I did? I've multiplied the other side by 2 straight away. Because I know I'm going to end up with v, so what do I want the half there for? Okay. Subbing in, v squared minus 25. There's v squared. Show that velocity is x squared plus 1. Hang on a sec. That's x squared plus 1 squared. V is x squared plus 1. Oh, hang on. I need to justify. Why did I choose the plus and not the minus? I'm saying, well, I know its velocity is greater than 0 in order to satisfy the initial conditions. Hence, find an expression for x in terms of t. dx to t, x squared plus 1. Separate the variables. T in this case is inverse tan of x. So t is inverse tan of x minus inverse tan of 2. But they've asked for an expression for x in terms of t, not t in terms of x. All right. Inverse tan of x is t plus inverse tan of 2. And again, a mere mortal would say, I'm happy with that. No. Tan plus tan and 1 minus tan. Okay, let's have a look at 6a.